Hello everyone, welcome to this video. My name is Sentinel-2. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to estimate water chlorophyll using Sentinel-2 in the Google Earth Engine platform. This tutorial can be used for all around the world. The data and the platform, both of them are open and freely available for all the users. So, now in the first step, you need to find your region of interest. The ROI or region of interest should be an inland water or a lake. For example, my area located in Nevada, it is Pyramid Lake, as you can see here. Then through the drawing tools available here, you can select your region of interest. For example, I'm gonna mark region of interest using mark tools or marker available here. Then if you want to have focus on the study area, just use map.center-object. Map.center-object for geometry helps you when the code is running, you will have focus on the study area. Then we need to call Sentinel-2 images. Make a new variable for Sentinel equals to, go to search places on dataset and type Sentinel-2. As you can see, two types of Sentinel is available. One of them level 1C and the next level 2A. Level 2A is atmospherically and radiometrically corrected, and this is the main option, should be for the spectral analysis or spectral indices. And as I'm going to use actually Sentinel spectral indices, that's why Sentinel-2A should be selected here. Level 1C is corrected only radiometrically, but you can use it as an alternative for the dates that Sentinel-2A is not available. Import it into the code, and here you have an image collection. So assigning image collection to the Sentinel, and then filter your data based on the period of time you want to do your study. For example, my reference here in the climateengine.org, in this address, as you can see, there is a reference about normalized difference chlorophyll index that shows how water chlorophyll changes in the Nevada, their area that I'm working in. So, and the index is normalized difference chlorophyll index equals to this relationship. And also here is the main reference for this tutorial. You can write the reference name or copy the reference name into the Google Scholar and then find the related papers. So the reference is attached below the video in the description box on my YouTube channel, and you can pick it up from there. And also the link of reference or the link of Climate Engine website is also attached that helps you directly come to this website and also get more information in this regard. So back to the code, and now I'm gonna call Sentinel-2 data for the period that this image taken from. As you can see, this image related to September 21. That's why I need to call all the data for 2021 September. So from early September to the late of September 2021 or 1st of October. Then filter your data based on region of interest or geometry already defined here. So in the next step, we need to call those of satellite data in which cloud cover is less than, for example, 45% to exclude cloudy images from processing. That's why make a new filter as less than Earth Engine .filter.lt. So Before talking about less than filter, let me show you something about the variable and also the properties and the bands included in the Sentinel variable. So here, print Sentinel, and in the right panel, you will have an image collection for September. As you can see, 24 images available for the selected region or marked region that we have here. So, as you can see here, for each image, we have 26 elements or 26 bands, but the only actually couple of bands are the targets for the spectral index analysis. Band 1 to band 12, these are the main bands that you must use for your process. So, and also here we have properties. And the property is something like metadata, allows you to get information about the data you are working with. For example, coefficients, azimuth, incident angle, and etc. And also the system time start and system time end. So these are the properties we have here. One of the information here is related to the amount of cloud cover in each image. As you can see, cloud cover assessment for the first data is 7%. So here I can make a less than filter to filter the data based on cloud cover percentage or cloudy pixel percentage, no difference. One of these variables should be selected. The filters help us to filter the data based on the properties we have here. For example, I'm gonna make a less than filter to filter out data based on cloud cover less than 10% to exclude cloudy images from processing. So that filter that's less than, for example. Here it is. First, we have the name of property, and then we will have a value less than, for example, 45. Run a code again, and as you can see, 22 elements remained for this region. In the next step, we need to calculate the value or the target spectral index or the value of chlorophyll over the water body. This is very important thing. So the NDCI stands with normalized difference chlorophyll index equals to a division relationship or a normalized relationship between the red edge 1, that is band number 5, and the red band, that is band number 4. So now we have 22 elements, or we have 22 images. Now I need to make a loop and then calculate NDCI. That map allows you to make a loop here. Inside the map, to do a certain calculation on each available images, you must have a function. Make a function like this, and each input image into a function should be called with a specific name. For example, IMG could be that specific name. So here, make a new variable, for example, bands, in the body part of function. From each input image, select all the main bands starting with B, but the rest of that is not matter. As you can see in the features, all the main bands starting with B from 1 to 12. So now I'm gonna select all the bands starting with B like that. So if you go to the data properties or data information by clicking on the link, you will have a lot of information about the data characteristic and also band information that you can see here. Suggest you to open it up into a new page, and here you can see the dataset is available since 2017. If you pick or if you are using with Sentinel-2 level 1C, in that case the data will be available since 2014. That is a longer period of time for the time series analysis. But after or since 2017, level 2A data is available, and it is a good opportunity to actually use this kind of data that is completely corrected and make you sure about the pre-processing accuracy. So, as you can see here, the scale value is same in all the band. So, just copy and paste it into the code and apply it using .multiply, just like that, and paste the scale factor. This is necessary for Sentinel-2 data. So then, for the first step, we need to calculate normalized difference water index, because it is important to actually differentiate the water body from the non-water bodies. So the NDWI stands with normalized difference water index that help us to differentiate between water and non-water pixels. From input bands already corrected, that normalized difference, you can calculate normalization relationship between near infrared and red. So the near infrared is band 8 and red is band 4 here. That rename the final band as NDWI. If you want to have water body as a separate, actually, if you want to have a binary layer for the water body that shows the water with value 1 and the non-water with value 0, in that case, you must have a threshold image or threshold variable included NDWI in which pixels greater than 0.1 selected. So NDWI greater than 0.1 makes a binary image in which water bodies have value 1 and non-water body pixels will have value 0. So then in the next step, I'm gonna calculate the NDCI, normalized difference chlorophyll index. From input bands, that's normalized difference. I'm gonna calculate the normalization relationship between first red edge, that is band number 5, and band red, or band number 4. Rename it to NDCI, normalized difference chlorophyll index. Finally, the function returns the NDCI only for the water bodies through the update mask threshold. Threshold is a binary image, as I said, that separated water body from the other phenomena or land covers. So the update mask helps you to get rid of extra pixels or non-water pixels in the NDCI and keep the NDCI values same for the water body. This is a very good, actually, ability that we have using update mask and binary image that is created to have only chlorophyll values for the water bodies. So then the final image must have some of the properties that are necessary for the time series analysis. Among the all metadata information or properties, system time start and system time end are the most important one, because we need these properties for the time series analysis in further steps. So here, that's why from all properties in the input image, I'm gonna have system time start and system time end with the output. Run a code here. In the right panel, again, you will have 22 elements in which NDCI is calculated for each date, and then in the properties, you will have system time start and system time end. Remember to save your code first and then select whole of the lake using a rectangle. So now I'm gonna go through the visualization process to see this pattern for the selected time or the selected month in this region. So here, using drawing tools available here and geometries, first make a new geometry, then go to the rectangle view. So try to select your region of interest like this, and then suggesting you to adjust center object based on geometry number 2, which provides a good view from your region of interest that helps you to see the lake actually from good point of view. So for the next step, we want to do visualization using map.addLayer. Couple of arguments in the map.addLayer considered. First is the target object, that is Sentinel data. If you want a stack layer, .toBand used. Using the two bands, you will have a stack layer that each band actually shows the NDCI for a single date. And if you want to clip it based on the region of interest based on geometry 2, that clipped geometry 2 is used. So visualization parameter should be empty for now, and the layer name in the layer setting will be NDCI, and the shown will be false. So meaning that we want to avoid automatic visualization. So because it highly reduces the speed of processing. Save your code now and click on Run. After a few moments, in the right panel, you will have an NDCI image. Turn off the geometries to have a better visual view, and then here, try to select images. For example, I'm gonna select the first one here with 90%. So since there is a problem here and the water body we don't have information about the water body. Seems something is wrong, and it is about NDWI. In the NDWI, actually I used NDVI relationship between near infrared and red. While in the NDWI, we should get relationship between band number 3, band green, and band near, and also the near infrared, or band number 8. So in that case, the problem will be solved. Now you can see I have the water body that's completely extracted or excluded from, separated from the other land covers. So as you can see here, all September images for that region is available, and it is a good opportunity to select each one of them and show the chlorophyll variation over the water bodies. For example, the first image related to September 1, I'm gonna select it and increase the contrast, and here you will have a final image. White pixels higher, actually here, the darker region shows lower chlorophyll, and also the white regions or regions with brighter color shows higher chlorophyll in the pixels. For example, now we have higher concentration in this part and this part, but in the middle it seems we don't have any, we can't see any dynamic chlorophyll values. So you can check different dates by this technique easily. The higher values, higher chlorophyll, and the lower values, lower chlorophyll. So these are the September images that you can see all of them separately to get understanding about how water chlorophyll changes. As you can see, the chlorophyll changing dynamically in this region, and you cannot see a same variation over the water bodies during the time. So I'm gonna find that image. As you can see, the range of values suddenly increased in this image. This is for September 19. No, this is for September 8. Sorry, it was my mistake. First digits 2021, 09, September 08. This is September 8, 2029. So if I click on apply, then you can see in this image, same as example we had before, the rate of chlorophyll A highly increased in this region because it's dynamically changing. So, and NDCI is a target index that helps us to use red edge band and red band to highlight chlorophyll variation over the water body. If you want to actually visualize it using some sort of color tables or palette, just go to the palette and use the color table like this. For example, I'm gonna have 3 color palettes from red, yellow, and green. There it is, and click on apply. Then you will have chlorophyll variation in the region of interest. So maybe you want to select only this image for the output. So this is also very simple technique. This is a question how we can pick or select just one image from the collection we have for September. So now we know the exact date for the output, or we can find it through the features we have here. But unfortunately, the image ID is missed because of processing we already done. But there is no problem. We can filter the data based on exact date of months. So now the target image equals to, from Sentinel data, I'm gonna make a new filter date to find the target. The target image belongs to September 8. So here 2021 September is the month, and also the day is September 8. And the end date will be one day after, 2021 September as month, and the day is day number 9. So if I print the target, in the right panel you will have 2 elements for this date. So there are 2 images. Again, we can do visualization for this region. So the target dot 2 bands here, clip based on geometry, and this is NDCI target image. Run the code again. Here you will have 2 NDCI images. Both of them are for a same day. So here, increase the contrast by a stretching technique and check the both images. As you can see, we have a same pattern in the both of images. The simplest way is getting an average to convert them to a single data. This is one scenario. For example, I can get an average like this and run the code. In this case, I will have one single image that shows the average value of chlorophyll from two images we had here. This is one scenario. But another scenario is, for example, here, if I back to the previous example here, we can make a stack layer using .2 bands, and then we can select one of them. For example, the first one I'm gonna select here. The first band from 2 bands, I'm gonna select the first one. This is another scenario that you can use to find your target data, or actually extract your target data from the other existing data that you have. So, but the question is how we can get export from this layer. This is also a very simple technique that couple of times repeated on my YouTube channel in different tutorials. As I mentioned before, exports.image. Exports.image to drive is a function allows us to save the output into a Google Drive, and then you can find the final data from the Google Drive and bring it into desktop software. Exports.image to drive. The image I'm gonna save is the target, just like that, but the target one, I'm gonna make an average from both, and then I'm gonna clip it based on the geometry or region of the interest. The next argument is description. The name of output layer is NDCI, and scale or pixel size for the output should be 20, because band number 5 has 20 meter spatial resolution. We have 2 bands in the NDCI. One of them is 10 meter, band 4, and one of them is 20 meter. In this situation, it is better to use 20 meter or bigger value for the pixel size that provides a higher quality images compared to when you want to actually use lower values like 10. The region of interest equals to geometry number 2, and the maximum pixels for each output TIFF layer equals to 1e13. This is the density of pixels, or the value the number of pixels you can have in each tile that you want to get export. The CRS, or coordinate system, could be WGS84, but you should write it like this: EPSG 4326. There it is. And also you can define a folder to save your results in. For example, I'm gonna make a folder as chlorophyll, and then I'm gonna see the output, or have the output in the folder entitled chlorophyll. Save the code and run it again. In the right panel, after a few moments, you will have NDCI layer that is going to save into chlorophyll folder, and clicking run. As you can see, the process of saving just started, and as you can see here, once the process of saving is done, the tab color turned to blue, such as the previous example I have here, and then we can pick it up from the Google Drive, and then you can open it up into the desktop software such as QGIS, ArcGIS, and etc. I hope you liked this tutorial, and I tried to show you how you can select the water bodies or exclude or how you can separate the water bodies from other surfaces, and how you can calculate normalized difference chlorophyll index. And also I will be appreciate if you follow my tutorials on your YouTube channel and share it with your community. Thank you for your attention.